Hello everyone. Today we are going to analyze a propped cantilever beam when it is subjected to an eccentric point load W at the distance of A from the fixed end. Let us keep the distance between the load and the propped end as B. The total length of the beam is given as L. In this analysis, first we are going to derive the expressions for the fixed end moment at A and the vertical reactions. Then we are going to draw the shear force and the bending moment diagrams. Then we are going to derive the expressions for the deflection under the point load, and we are going to find the maximum deflection and its location. Finally, we are going to derive the expressions for the slope under the point load and at the propped end. In this analysis, first we have to find the prop reaction RB. For that, we can use this condition. In the point B, the upward deflection due to RB will be equal to the downward deflection due to the load W. To find these deflections, we can use the moment area method. The formula to find the deflection in the moment area method is area x bar upon EI. Using this formula, we can make this expression. We can eliminate EI. Finally, we are getting this expression. Area 1 x bar 1 is equal to area 2 x bar 2. Now we are going to draw the bending moment diagrams. First, let us find the bending moment values. We have to find the bending moment values about the point A. In this case, we are moving towards left hand side. Clockwise will be negative and anti-clockwise will be positive. First, let us take RB. It is acting in the anti-clockwise direction, so that will be positive, and the distance is L. So RB into L. Since it is positive, the diagram should be positive. The load W is acting in the clockwise direction, so that it will be negative, and the distance is A. W into A, we will get WA. We know that it is negative. Now let us find area 1 x1 bar. This is a triangle. We know the formula for the area of a triangle, half into BH. Here B is L and the height is RBL. The centroid distance is 2 by 3 into L. Now let us find area 2 x2 bar. This is also a triangle. We know the formula for the area of a triangle, half into BH. Here B is A and the height is WA. The centroid distance is 2 by 3 into A, but we are finding the moment area up to the point B, so we have to add this distance. This distance is B, so x2 bar is 2 by 3 A plus B. We know that area 1 x1 bar is equal to area 2 x2 bar. Just before we have made the expressions for both of them, let us apply them. We can eliminate 2. L into L into L, we will get L cube. A into A, we will get A square. Here we can take LCM. 3 into B, we will get 3B. We can write 3B as 2B plus B. In these two terms, 2 is common. We can take 2 outside. So we will get 2 into A plus B. A plus B is L. So 2L. We know that B is L minus A. Let us apply that. 2L plus L, we will get 3L. We can take L cube upon 3 on the other side. It will come inversely. 2 3s are 6. Finally, for RB, we have made an expression WA square upon 2L cube into 3L minus A. Now let us apply the rule sigma V is equal to 0 and find RA. RA and RB are acting upwards, so both of them are positive. W is acting downwards, so it is negative. We can take these two terms on the other side. They will come with the change of signs. For these two terms, we can take LCM. 2L cube into W, we will get 2L cube W. We know that A is L minus B. So for A square, we can apply L minus B the whole square. And for A, we can apply L minus B. Here, we can use the formula A minus B the whole square. A square minus 2AB plus B square. Here A is L and B is B. Using the formula, we will get this. Then we can multiply these two terms. When we do that, we will get this. We can eliminate these two terms. Then we can take a negative sign inside the bracket. So this will become negative, this will become negative, this will become positive, and this will become negative. Then we can eliminate 2L cube minus BL square plus 4BL square. We will get 3BL square. We can take B outside. So here it will be B square. Finally, we have made an expression for RA. Now let us apply the rule sigma m is equal to 0 and find MA. From the point B, I am going to take movement about A. In this case, I am moving towards left hand side. Clockwise will be negative and anti-clockwise will be positive. RB is acting in the anti-clockwise direction, so that will be positive and the distance is L. The load W is acting in the clockwise direction, so that will be negative and the distance is A. Let us assume that MA is acting in the anti-clockwise direction, so that it will be positive. We can take these two terms on the other side. We can eliminate this L, here it will be square. We can take WA outside, then we will get this. For both of these terms, we can take LCM. 1 into 2L square, we will get 2L square. We can take 2L square outside and then let us multiply minus A with 3L minus A. We will get this. We can write 2L square is equal to L square plus L square. And we can write minus 3AL is equal to minus 2AL minus AL. Here we have A minus B the whole square formula. We know that A minus B the whole square is equal to A square minus 2AB plus B square. Here A is L and B is A. So for this term we can write L minus A the whole square. We know that L minus A is B, so it will become B square. We know that A is equal to L minus B, so instead of A, let us apply L minus B. Let us multiply L minus B with L, we will get L square minus BL. Then take the negative sign inside, so L square become negative and BL becomes positive. We can eliminate L square. We can take B outside, so here we will have L plus B. We know the formula A square minus B square is equal to A plus B into A minus B. So L minus B into L plus B becomes L square minus B square. Finally, we have made an expression for MA. Now we are going to draw the shear force diagram. From the point A up to the point C, we can use right hand side rule. Upwards will be positive and downwards will be negative. From the point B up to the point C, we can use left hand side rule. Upwards will be negative and downwards will be positive. So we can easily find the shear force values. Here you can see the shear force diagram. Now let us find the bending moment values. The point B is a simply supported end, so the bending moment in the point B will be 0. To find bending moment at A, let us use right hand side rule. Clockwise will be positive and anti-clockwise will be negative. MA is acting in the anti-clockwise direction, so that it will be negative. To find the moment in the point C, let us use left-hand side rule. Clockwise will be negative and anti-clockwise will be positive. Or B is acting in the anti-clockwise direction so that it will be positive and the distance is B. Finally, for the bending moment at C, we will get this. Here you can see the bending moment diagram. In this point, the bending moment is 0. This point is called the point of contraflexure. Let us make a section in this point at a distance of x from the point A. Let us find the moment in this point and find x. Let us use right hand side rule. MA is acting in the anti-clockwise direction so that it will be negative. RA is acting in the clockwise direction so that it will be positive and the distance is x. We can take this term on the other side so it will become positive. We can eliminate WB 2 and L square. We can take these two terms on the other side, they will come inversely. Let us apply x here. Suppose we have to find the point of contraflexure from the point B. We have to subtract this by L. We can multiply L with this term, we will get this. For these two terms, we can take LCM. When we multiply L with this, we will get this. Let us take the negative sign inside. L cube becomes negative, minus b square L becomes positive. We can eliminate these two terms. 3L cube minus L cube, we will get 2L cube. Let us apply the expression. Now we are going to find the slope and deflection. In the point A, there is a fixed support. So the slope and deflection in the point A will be 0. In the point B, there is a vertical support. So the deflection in the point B will be 0. Now we are going to find the slope in the point B and the slope and deflection in the point C. For that, we are going to use Macaulay's method. In that method, we have to make sections. In this beam, there are two different parts, AC and CB. So we have to make two sections, one section in CB and one section in AC. You can see that I have made two sections, the first section in CB and the second section in AC. I have made both of the sections at the distance of x from the point B. Now let us find the moments in the sections. We are going to find the moments about the sections from the point B. In this case, we are moving towards left hand side. Clockwise will be negative and anti-clockwise will be positive. RB is acting in the anti-clockwise direction so that it will be positive and the distance is x. The point load W is acting in the clockwise direction so that it will be negative. For this load, we have to take this distance. This distance is x minus b. These two terms should be separated by the dotted line because this term is only applicable beyond the point C. From the point B up to the point C, only we have to consider this. Let us equate the moment about the sections to EI d square y upon dx square. Now let us integrate on both of the sides. For integrating x, we can use this formula, and for integrating x minus b, we can use this formula. When we integrate d square y upon dx square, we will get dy upon dx. When we integrate x, we will get x square upon 2. When we integrate x minus b, we will get x minus b the whole square by 2. C1 is the constant. 2 into 2, we will get 4. Let us integrate this equation again. When we integrate dy upon dx, we will get y. When we integrate x square, we will get x cube upon 3. When we integrate x minus b the whole square, we will get x minus b the whole cube by 3. 3 into 2, we will get 6. When we integrate C1, we will get C1x. C2 is the new constant. 3 into 4, we will get 12. We know that in the point A, there is a fixed support. In the fixed support, there will be no slope. So when x is L, dy upon dx is 0. Let us apply the values of x and dy upon dx in this equation. We know that L minus b is A. We can eliminate L square. Here it will be L. Let us take these two terms on the other side. They will come with the change of signs. From both of these, let us take minus WA square upon 2 outside. For these two terms, let us take LCM. Minus 1 into 2L, we will get minus 2L. 2 into 2L, we will get 4L. Minus 2L plus 3L, we will get L. L minus A, we will get B. So for C1, we are getting this. In the point B, there is a vertical support. So there will be no deflection. So when x is 0, y will be 0. In this equation, let us apply the values of x and y. When we do that, we should not consider this term because this term is only applicable beyond the point C. Here we are applying the condition in the point B only. So we should not consider this term. Only we have to apply these values here. When we do that, for C2, we are getting 0. We have found C1 and C2. Let us apply the value of C1 in the slope equation. When we do that, we will get this. Let us keep this equation as number 1. Let us apply the values of C1 and C2 in the deflection equation. When we do that, we are getting this. Let us keep this equation as number 2. Now let us take the first equation and find the slope values. First, let us find the slope in the propped end. We know that dy upon dx is the slope. Since we are finding the slope in the point B, let us denote dy upon dx as theta b. In the propped end, that is the point B, the value of x is 0. So in this equation, we have to apply x is 0. We should not consider this term. Finally, for theta b, we are getting this. Now let us find the slope under the point load, that is in the point C. So let us denote the slope as theta c. In the point C, the value of x is b. So in this equation, instead of x, we have to apply b. Here also, we should not consider this. From both of these terms, we can take w a square b upon 4l outside. For these two terms, we can take LCM. L square into 1, we will get L square. L into L square, we will get L cube. We know that L is A plus B. So instead of L, let us apply A plus B. Let us multiply A plus B with 3B. When we do that, we will get this. Here we can use the formula A plus B the whole square is equal to A square plus 2AB plus B square. Then let us take the negative sign inside. So all of them will get negative. We can eliminate 3AB minus AB and minus 2AB. 3B square minus B square, we will get 2B square. Then we have minus A square. Finally, for theta c, we are getting this. Now we are going to find the deflection under the point load. Let us take the deflection equation. We know that under the point load, the value of x is b. So instead of x, we have to apply b. No need to consider this term. Here we will get b cube. Here b into b, we will get b square. Let us take w a square b square upon 4l outside. Then we will get this. For these two terms, we can take LCM. 3l square into 1, we will get 3l square. 4 into 3, we will get 12. L into L square, we will get L cube. We know that B is L minus A. So instead of B, let us apply L minus A. Let us multiply these two terms, we will get this. And let us multiply minus A with L minus A, we will get this. We can eliminate 3L square. Minus 3LA minus LA, we will get minus 4LA. From here, let us take minus A outside. So here we will have negative sign. A into A square, we will get A cube. 4L becomes positive and A becomes negative. For the deflection, we will get a negative value. That means it is acting downwards. Now we are going to find the maximum deflection. We know that when the deflection is maximum, the slope will be 0. Let us take the slope equation and equate that to 0. When we take this equation, we should not consider this. Let us take this term on the other side, so it will come as positive. We can eliminate WA square upon 4. Also, we can eliminate L. Here it will be square. Finally, for x square, we will get this. Then let us take square root on both of the sides. We can take L square outside. Outside, it will come as L. We have found the location of maximum deflection. Now, let us take the deflection equation. In this equation, instead of x, let us apply this. We can take L cube outside and then eliminate L cube. Here we can eliminate L. Then we can split this cube root into two parts. This term will come out of the root. We can eliminate these two terms. We can add these two terms. 1 by 12 minus 1 by 4. We will get minus 1 by 6. For the maximum deflection, we have got a negative value. That means the deflection is downwards. This maximum deflection formula is only applicable when B is more than 0.414 L. Now we are going to find the maximum deflection when B is less than 0.414 L. Let us take the bending moment diagram. We know that this is the point of Contra flexure. We found the location of point of Contra flexure. We know this is a triangle. On the right side also, we have to select a similar triangle with the same distance. So the height of the triangle also will be same. In this section, the maximum deflection will occur. Let us use the moment area method to find the deflection. We have to find area x bar. Let us take this triangle. We know the area formula of a triangle, half into BH. Since the bending moment is negative, we have to apply the formula with the negative sign. The centroid distance is 2 by 3 into B, but we are finding the deflection in this section, so we have to add this distance also. This is B, so 2 upon 3 into B plus B. For this triangle, the area is half into BH. The centroid distance is 1 by 3 into B. We can take minus half into BH outside. When we add these three, we will get 4 upon 3B. 2 2s are 4. B into B, we will get B square. Now, in this formula, let us apply the values. B is this one. Let us apply that. And height is this one. Let us apply that. We can eliminate 2L square. We can multiply these two. When we do that, we will get a cube. We know the formula to find the deflection in the moment area method, that is area x bar upon EI. We have found area x bar, only we have to apply EI. For the maximum deflection, we will get a negative value. That means it is a downward deflection. We know the location of maximum deflection, 2 into L square minus B square upon 3L square minus B square. Suppose we have to find this location from the right side. We have to subtract this by L. For both of these terms, we can take LCM. We can multiply L with this. When we do that, we will get this. 3L cube minus 2L cube, we will get L cube, minus LB square plus 2LB square, we will get LB square. From here, we can take L outside. So, in this propped cantilever beam, the maximum deflection is either this or this. This is according to the distance B. If B is less than 0.414 L, we have to use this formula, and this is the location. If B is more than 0.414 L, we have to use this formula, and this is the location. Now we are going to end this session. Thank you for watching this video.